for questions. Okay, so then with that out of the way, we can start talking about the math. So over the next few lectures, we're going to talk about some applications of derivatives and some ways that you can use derivatives to learn information about a function and sort of what derivatives are helping us accomplish. So one thing that they do is they help us solve optimization problems. So optimization problems are anytime you're asking a question that can be phrased as what is the maximum or minimum value of a function. So some real life examples of this might be something like, in some cases, it's obvious what the function that you're asking about is, and sometimes it's not. So, oh my gosh, the projector is still really moving. Not great. Okay, so one example is like, what is the highest temperature that's ever been recorded in history? So somewhere out there, there might be, let's say just for Nashville, there's like, someone's been recording at every time what is the temperature, and you can look at that function and wonder what was the hottest temperature ever recorded. Another example is, and this is less obvious what the function is, but like, let's say you're given some amount, a fixed quantity of fencing material, like something to build a fence out of, and you want to know what is the largest area that I can enclose in a rectangular fence given this fixed amount of material. And so we can solve questions like that as well. So given some fencing material, what is the largest rectangular area that can be enclosed? Okay, so is this just awful? Can you guys read it? Should I switch to the Blackboard? Would that be better? Blackboard? Let me see if I have chalk. Okay, I don't have chalk, but so we'll stick with this. But unless there's a, yeah. Okay, so I will bring chalk next time, and I'll also like let someone know that there's an issue with the projector. So hopefully we can get this fixed before next class. Okay, so let's look at some examples in a picture. So let's say I have some function and it's defined on an interval, a closed interval from A to B. And let's say it looks something like this. So in this interval, we have here is the largest value that the function attains. This is the maximum. And then here's the smallest value, which is called this minimum. And you can also have, so since this is the maximum value that this function attains across the whole interval, you call that an absolute maximum, or sometimes people also say global maximum. So absolute. And same thing for minimum, you have absolute minimum. And then there's also an idea of a local maximum or minimum. So that's like, this temperature was hotter than all the other days this month or something like that. So for a picture of that, we might have something like, so here you have like a little hump and a little valley, and this value might still be interesting because it's larger than all of its neighbors. And same thing here, you may want to know about this value because it's the minimum among all of its neighbors. And these are called local maximum and local minimum. So I'll just write down a precise definition for these things. We'll have a definition. So after I define them, we'll look at some examples, and then what we'll do is we'll look at something called the extreme value theorem that tells you under what situations you know that these things exist. And then we will discuss how to actually find them. Okay, so here's the definition. So I'm gonna let C be a number in the domain, which I'll call capital D, of a function f. Then I'll say that the value f of c is an absolute maximum of f on this domain D if f of c is greater than or equal to f of x for all x in D. Okay, so if I look at the value f of x for every element x in the domain, and I find that f of c is the biggest among all of those, then we say that f of c is an absolute maximum. Okay, are there questions about that? Okay, so I'll write down the analogous statement for minimum. So f of c is an absolute minimum of the function f on its domain D if, and now we'll just flip the inequality. So we want to see that f of c is the smallest among all f of x's for any x in the domain. Okay, so the definitions for the local maximum and minimum are a little bit trickier. So here's how those look. So we'll say that f of c is a local maximum if there's an open interval surrounding c where f of c is the largest value across all x's in that open interval. So we'll say f of c, I'll write it down, is a local maximum if there is an open interval, let's say A to B. We want this to be a subset of D. And we also want the interval to contain C, right? And we want to see that f of C is the largest value that f attains on that interval. So here's how I would write that. F of C is greater than or equal to f of x for all x's in the interval a to b. Okay, I'll draw a picture so you can see how that looks. So I'll draw something similar to the function I had before. That was terrible. Okay. Okay, so let's say here's my value C. Okay, and we want to check if this thing is a local maximum. So I need to decide if there is an open interval AB contained in the domain D, which in this case, I'll make a domain. So let's say this whole thing is D. Okay, so I need to find an interval contained in there such that the interval contains C and f of C is the biggest value that f attains on that interval. So what I can do is just take a little interval around C, and we'll find that f of C is the biggest value on that interval. So let's take A to be something like this. Is yellow just horrible? I feel like this is... Colors are just making this even worse, I think. Okay, so if we look across this interval A to B, f of C is the largest value that the function attains on that interval. Okay, are there questions? And then there's an analogous definition for local minimum. I'm just gonna copy this. So we'll say that this is a local minimum if there is an open interval containing C such that, and now all I need to do is just flip this inequality. So f of C is less than or equal to f of x for all x in D. Okay, good. So let's look at an example. So I'll just draw a function and we'll label the absolute max, absolute min, local maxes, and local mins. Okay, so it's gonna, our domain will not be the whole thing, it'll be something like this. Okay, so the domain D looks like this. It's this interval. Okay, so what are the absolute max, absolute min, local maxes, and local mins of this function? I can just start pointing to some of them and see what they are. What is that one? You say local min. Okay, so this one's a local min. What is this one? Yeah, so this is an absolute max. Is it a local max? So it's actually not, because there's no open interval that's contained inside of the domain where, you know, this is the maximum value of the function, right? So I can't stick an open interval around this point because the interval will state the domain. So this one is an absolute max, but not a local max. Does that make sense? Okay, what about this one? Yeah, that's a local max. What about that? And is it local? Yes. Okay, yeah, so this one is an absolute minimum and it's a local minimum. Okay, so we get this one is local max. This one is global, or yeah, I'll say absolute. Absolute min and local min. And then what about this point? That one's nothing, right? Because it's not a local anything because it's right up at the end of this interval. So we can't make an open interval that contains it. And then also it's not you know, the absolute maximum. Okay, so this point is nothing. Are there questions about that example? Yeah. Yeah, so, okay, so it's not an absolute max, right? Because there's something that's bigger than it. And it's also not a local max because I can't, there's no open interval containing it that's also contained in the domain. Other questions? Yeah.
Maybe you're not.
Yes. Yeah. So we'll talk about that. Yeah. Are there other questions? Okay, so here's like the question. Is when do we have these are all just like called extreme values. So when do we have extreme values? As in, when am I guaranteed that my function somewhere does have a low or an absolute maximum or an absolute minimum? And I'll write down the theorem statement and then we'll probe it a little bit. So here's the statement of the theorem. So this is called the extreme value theorem. So it says the following: if f is a continuous function on a closed interval AB, oops. Okay, so there's a lot of hypotheses here, right? Like we're assuming that the function is continuous and also that its domain is a closed interval. So if f is a continuous function on a closed interval, then f attains an absolute minimum I'll call this f of c and an absolute maximum f of d for some c and d that came from the interval. Okay, so if our function is continuous and the domain is a closed interval, then we're guaranteed that the function has an absolute maximum and an absolute minimum on that closed interval. Okay, so what I want you to do is the following. So what I want you to do is, so here's like a exercise. Try to make a counterexample to this statement. So what I mean by that is try to think of a function that satisfies the hypotheses, but doesn't have a maximum or minimum. So just like try to break it. And as you come up with counterexamples, then try to understand, why does my counterexample actually not break the theorem? Like, why does my counterexample not actually count? So part one, try to make counterexamples. And break the theorem. And part two, then understand why the counterexamples don't work. Okay, so I'll give you like 5 minutes to think about this, and feel free to discuss with each other and share your counterexamples, or if you can't figure out why your counterexample doesn't work, then you can ask your friend. But yeah, go ahead and take like 5 minutes to think about this.
Well, or do they ever have? Well, I guess it never would be. So unless you do something that was positive, like you're lower than
Okay, didn't anyone break the extreme value theorem? Did anyone come up with a counterexample? Yeah.
We didn't come up with like any counterexamples, but we have a question.
Yeah.
Like a horizontal line. Would that mean every point is not?
Yes, yeah, because in the definition, it's like a greater than or equal, yeah. Yeah, good question. Other, anyone come up with an example? Yeah,
If you have a sine function or like whatever, if you set the intervals as like 0 to 5, so you have like multiple or like
Yeah.
It really matter. But would you have two different absolute maxes or two different values?
yeah, so you can have multiple absolute maxes, yeah, as long as they're all the same value. So like in your example, yeah, if you have like, you're looking at the function sine x across a large interval, you'll have multiple places where you hit the value 1, which is the absolute maximum of the function. And so that would just be true for multiple inputs, yeah. Okay, what's an example to show why we need this hypothesis of continuous? So can you think of a function that does not have, say, an absolute maximum and it's discontinuous and it's defined on a closed interval? Yeah. Yeah, so here's the request. Defined on a closed interval, not continuous and does not have an absolute maximum. Yeah. So, I think that one would be an example for why you need a closed interval for this to be true, right? So like the x values have to come from a closed interval. So what does cosecant look like? So yeah, that's not defined at all of those values. We have a total asset.
All right.
Yeah, but okay, so that was going to be my second question. So that's like an example for why the interval has to be closed. So cosecant x, right, it shoots off to infinity, and so you don't have an absolute maximum anywhere on that interval. So what's an example for why you need the function to be continuous? And then think of one. Here's the one that I had. So here's the example. Why the function must be continuous. So let's say we're defined on like the interval from 0 to 1. And let's say the function is like a line going up to here, and then once we get to 0, it has a hole, and then it's just redefined at that value to be some other number. So this is like some piecewise function. It's clearly not continuous. but it also doesn't have an absolute maximum on that interval because I just plucked out the thing that would be the absolute maximum.
If something with imaginary numbers like this,
Maybe, like, what are you thinking of?
like if there's a function like f of x equals x times I. But I don't know, since you can't like graph it, I don't know. It's a perfect example.
Yeah, we're only talking about like functions of real numbers from the reals to the reals. Yeah. Yeah.
So the problem here is just that, yeah, sort of can't specify. a small-
Yeah, so like if you picked a value that you're like, okay, maybe this is the maximum, there's always gonna be something else to the left of that that would be at a higher value. But yeah, yeah.
You just make it a limit.
Right, so like, you know, the limit as x approaches 0 from the right of this function does get to some number, right? And that's like what you want the maximum to be, but the function actually never achieves that value. Yeah. Okay, so back to the statement of this theorem. So it feels like it's intuitively plausible, hopefully, by failure to like come up with a counterexample. But it's actually a little bit tricky to prove it. And you can understand the proof, but it's a little bit just long. So we're not going to do it, but if you are interested, it is written in the little book of limits and continuity. I think it's like 2 pages or something like that. So if you wanted to read the proof of this theorem, you could go and look there to see how that's done. But hopefully just by kind of like probing the theorem a little bit, you find it believable at least. Do you guys do you believe the theorem? Yeah, okay. And not just because I told you it was true. Okay, so how do we actually find extreme values? Okay, so thinking about the picture, so now that we know that they exist, like thinking about this picture, what are the candidates for the extreme values? Well, definitely the endpoints could be extreme values, and then the other ones that could be extreme values are also all of the local maxes and mins, right? So these are our candidates for the extreme values. So all the local maxes and mins, and then also the endpoints. And so basically how you find extreme values is that you will round up all of your candidates and then look among those to see which one actually has the largest value or the smallest value. And I think at this point, it might not be clear how to actually find these. And there's a theorem that will help us with this. And this is called Fermat's theorem. Not to be confused with Fermat's last theorem, which is a famous math problem, but this is just Fermat's theorem. So if a function f has a local maximum or local minimum, at some number c, then either there's two possibilities. One is the value of the derivative at C is equal to 0, or the value of the derivative does not exist. Okay, so thinking about our pictures, so like let me give an example for this one. So if our function looks something like that, I think it is plausible that at this highest value, we're gonna see that the derivative is 0, right? Just looking at the picture, that makes sense. The tangent line is has slope 0, and we'll prove why that has to be true. Or it could not exist. So here's how that might look. Think about like the absolute value function, right? The derivative at 0 does not exist, but this would still be a local min. It actually is a global min if that's the problem. So something like that. Draw a little tangent line here. Okay, so if I want to know what are the local maxes and the local mins, this theorem tells me that I have to find the places where the derivative does not exist, and I need to find the places where the derivative is 0. Okay, so luckily for us, Fermat did prove this theorem. So let me show you guys how that goes. Okay, so we'll just prove it for local maxes, but the proof will be the same for local mins. So let's suppose C is a local max. Okay, so if I want to prove an or statement like this, so we have, we want to say that something with the derivative, either it does not exist or it is 0. It is sufficient to prove the following. So we'll just assume that the derivative does exist and then show that it's equal to 0. Right, so let me write this down. So we will do the following. Assume f prime of C does exist and show it must be 0. Right, so that shows that either f prime of C does not exist or it is 0, because if I have a value C, the derivative could not exist, right? So that could happen, and then we're in this case and the theorem is true. Or it does not, or it does exist, and then the proof will work and show us that the derivative has to be 0. Does that make sense? So this is all we need to show. So we'll suppose that the derivative at C does exist. Okay, so since C is a local max, we have the following inequality. So we have f of C is greater than or equal to f of C plus h for small h's. Right? So in a small area around C, if I plug in a small positive or negative value for h, we know that the maximum around there is going to be f of C. Are we happy with this inequality? Okay, so I'll just rearrange this. So we get that f of C plus h minus f of C is less than or equal to 0, just by rearranging the inequality. Okay, so then what I'm gonna do, I'm trying to work my way towards something that looks like the derivative. So I'll divide both sides of this inequality by h. H could be positive or negative. And so I'm gonna have two cases, because if you divide by a negative number, that will flip the inequality. So I'm gonna divide both sides by h, and there's two cases. So if h is greater than 0, we get the following. So we can just divide by h without flipping the inequality. So we get f of c plus h minus f of c divided by h is less than or equal to 0. And if h is negative, then I have to flip the inequality. So I get f of c plus h minus f of c divided by h is greater than or equal to 0. Okay, so are we so far so good? So now what I'm gonna do is take the limits of these, right? Because the limit of this as h approaches 0 from the right. And this one, limit as h approaches 0 from the left. And since we know that the derivative exists, right? We know that those two limits have to be in agreement with one another. So let me look at those two limits. So we know that f prime of c exists, which means that the limit as h approaches 0 of this thing exists. So here's what we get when we look at those two limits. So I'm going to just string together a bunch of inequalities, and I'm going to call this equation 1, and I'll call this equation 2. Okay, so I know that 0 is less than or equal to the limit as h approaches 0 from the left of f of c plus h minus f of c divided by h. So that's by inequality 2, right? So I just took inequality 2 and took the limit as h approaches 0 of both sides to get this inequality. And then since the limit exists, the left-hand limit and the right-hand limit have to agree with one another. So this is equal to the limit as h approaches 0 from the right of f of c plus h minus f of c divided by h. So this is by limit exists. And then here, I'll just apply inequality 1. So I get that this is less than or equal to 0 by inequality 1. Good with this? Okay, so then what can we conclude? So we had this thing called the squeeze theorem. You guys remember that? We used it briefly in a different proof, where if I've tracked a limit in between two values, then that means that the limit has to equal that value. So here I have this limit that I know is both greater than 0 and less than 0. So the only option is that that limit is equal to 0. So by the squeeze theorem, we get that the limit as h approaches 0, f of c plus h minus f of c divided by h, which is equal to the derivative at c. This is equal to 0. And so that proves the theorem. Okay, are there questions about this? So we will end here for today, and next time we'll see how to use this to actually find the extreme values of a function. We'll do some example problems. I'll see you guys on Wednesday. Yeah, like within the hour probably.